All right, good morning, everybody. So in the end of the last lecture, we were talking about method preconditions and postconditions. And we got to the postcondition part. So remember what a postcondition is. A postcondition is a condition that the method must ensure is true immediately after the method finishes running. Right, so the postcondition of a method is basically what the method says it will do. So the postcondition is what the method says or what computation the method says it will perform. Right, now technically it's a condition. So it has to be something that you can write down as a, that ends up being true or false. If your postcondition is not true, then there's something wrong with what you've done inside the method. Right? Now, for a non-static method, a postcondition can involve something about the return value. Right? So if the method returns a value, there might be some condition on the value that's returned. If the method changes the state of the object that was used to call the method, then the postconditions will involve the fields of the object. Right? And if the method changes the state of an object that was passed to it as an argument, then the postcondition involves the object that was passed to the argument, passed as an argument to the method. Now, normally the postconditions for a Java method are not described as true conditions, right? So they're not expressed as true-false expressions. Instead, they're described as plain old English, right? And so here's our method x in the point2 class, right? So remember, this method just returns the x coordinate of the point. Right? And so normally what you see is a description of the method, right? This one returns a value, so there's a return, there's an @return tag, right? That describes what the method is supposed to do, right? Now notice what's not here. What's not here is the actual postconditions of this method, right? So it is possible, but it's usually very awkward to express postconditions as actual conditions, not just in Java, but in any programming language, right? So if you look at this method here and you ask yourself, so what are the postconditions for this method, right? So if you just look at the plain old English, it says it returns the x coordinate of this point, right? But there's a bunch of other stuff, there are other things that you have to consider in order to completely state the postcondition of this method, right? So what does the method do? It just returns the x coordinate of the point, right? So you have to ask yourself, what does it not do, right? Well, it doesn't change the coordinates of this point, right? So in other words, part of the postcondition of this method is that the state of the point is unchanged when you call the method, right? P.x does not change the coordinates of the point P. Right? Now, what else is involved in this postcondition? Well, it has to return the x coordinate of the point that was used to call the method, right? But there's a little bit more here, right? It has to return the x coordinate of the point, right? X coordinate of the point at the time when the method was called, right? These two are actually related, right? The state of the point is unchanged, right? Returning the x coordinate of the point at the time when the method was called, these two conditions here are actually related. So you can actually write all of this out as a condition, right? So first of all, I'm going to rewrite the method. Notice that it becomes very complicated, right? So if I want to state the postcondition of this method, right, I need somehow to capture the fact that the state of the point is unchanged, right? So in other words, I need the x coordinate and the y coordinate of the point immediately after the method was called, right? So the very first thing in the method, I'm going to make a record of, right? I'm going to remember what x and y for this point are, right? So I'm going to create a local variable old x and a local variable old y. I'm going to set it to this x and this y, right? And I'm going to make sure that those values can never change. So I'm going to mark these two variables as final, right? So once I assign a value to old x, old x never changes. Once I assign a value to old y never changes. Right? Okay, so I can now remember what are the coordinates of the point when this method was called. Right? So now I can write the post condition, right, which would be which is the thing which is evaluated immediately after the method is called. Right? Now there's a return statement here, so I would like to evaluate the post condition here. I can't actually evaluate it here in Java because you can't put any code after a return statement. Right? But conceptually, this is where you want to check the post condition. Right? And so the post condition that says the state of the point is unchanged is, right, this x, right, the current state of the point is equal to the old x, the state of the point when the method was called, right? And the current y coordinate of the point, this y, is equal to the y coordinate of the point when the method was called, right, back here. So that checks, is the state of the point unchanged? Now I'd also like to check that the return value is equal to the x coordinate of the point at the time when the method was called, right? So I want to check if the result, I guess technically this is if the result is equal to old x. So this should be old, well, this x equals old x is true, up here is true anyway. So I want to check, is the result equal to the actual x coordinate of the point, right? Notice that to check if the result is equal to the x coordinate of the point, right, I need to know what the result is, right? I'm going to mark it as final, so I can't actually change, I cannot accidentally change the value of result, right? And so notice here that the expressing this post condition for this trivial method, right, is extremely complicated, right? Almost no one would come up with this post condition the first time you look at this method, right? You have to look at the state of the point when the method was called, right? And then you want to look at the state of the point immediately after the method returns, right? And so this is one of the reasons why post conditions aren't normally expressed as actual conditions, right? They're sort of described in English or in the description of the method without resorting to the strict mathematical expression of the post condition. Right? Okay, so what about a method that changes the state of the point? So here's the method that changes the x coordinate of the point. Right? It changes the x coordinate of the point to new x. Right? Again, if you read the description of the method, the post conditions are kind of hidden or sort of expressed in the description of the method. Right? It says that the x coordinate of the point is changed to the specified value. Right? It says that it returns a reference to the point that was used to call the method. What's not said is that the y coordinate of the point doesn't change. Right? But that's all part of the post condition. Right? So the post condition for that method here, right, the x coordinate of the point after the method returns is equal to the value of the argument that was passed to the method. Right? So in other words, the x coordinate of the point is equal to new x, right? For the value of new x that was actually passed to the method, right? The y coordinate of the point is unchanged by the method, right? And you also, of course, there's the return value. So the return value is equal to a reference to the point that was used to call the method, right? Once again, you could code up the method so that you could express the post condition, right? So this x equals param x. So what's param x? So param x is equal to a copy of new x back here, right? So in the very first line of code, I'm going to remember what is the value of new x, and I'm going to stash that in param x. Right? Now the reason why I'm doing this here is because inside the method, right? Inside the method, you can actually change the value of new x, right? So somewhere like here, I could write new x equals something, right? Which would change the value of the argument that was passed to the method, right? If I want to test whether or not the current x coordinate of the point was equal to the actual value of new x when the method was called, I need to remember what that value is, right? So that's what this variable is doing here, right? I want to check that the y coordinate of the point is unchanged. So at the very beginning of the method, I need to record what is the value of the y coordinate. Right? And at the end of the method, I can check if this y is equal to old y. Right? The last part is a reference to the point that was used to call the method returned. That's pretty easy to check. Right? I can just check if this equals result. Right? Remember, this is a reference to the point that was used to call the method. Right? Result is the result that was returned. Right? And so I can check that fairly easily. Right? But notice once again, the post condition is very awkward to express. The only way to express the post condition is to add some extra code into the method so that I can check things. Oh, here's an example of why you need to remember what param x is. Right? There's nothing stopping someone from changing the value of new x inside the method. Right? And so this particular implementation changes new x to 1 and then sets this x to new x, right? Which ends up setting this x to 1. Right? So this method's incorrect. Right? If you were to check that post condition is false in this case, right? Which indicates that there's something wrong with your method. Right? And so a feature of the Java language is that if you have a parameter, like new x, right, that's not final, then inside the method you can actually change the value of new x, right? Because this parameter new x is just a variable for the method. Okay, so notice that you can't actually check the post condition here, right? Because you want to check the post condition at the point when the method finishes, right? That's after the return statement. I can't put any code in after the return statement. So there's actually no way to there's no proper way to check that post condition if you wanted to, right? So the best that you can do, well, one of the things that you could do is insert an if statement into your code before the return statement, right? So for example, before I return the result, right, I can stick in an if statement and check the post condition here, right? If the post condition is false, I know that something has gone wrong inside the method and I can throw an exception like that. Right? This isn't perfect because you really want to check the post condition here. This is the best that we can do. There is an alternative to this. I'm going to skip this slide, this one and the next one. So I don't think this is actually important for you to know. If you're curious about how you might do this, you can read this slide and the next. And that one here. All I want to say to complete this part of the lecture is that you might wonder why I'm talking about doing stuff like this, right? So normally you wouldn't write code like this. You wouldn't write your method like this, right? No one's going to write the set method like this, right? You're just going to write set like that. Oops, sorry, like that, right? So this is the way you're going to write your methods. Yes. Right? I'm showing you this because there's a course later on in 4th year, I think, that talks about how can you informally prove that code is correct, right? So just think about that for a second, right? So all of the programming you've done so far in CISC121 and 124, right? You write some code, you might run it to look at the output, and then you might look at the output and say, yeah, that looks right, right? You don't really know that your code is correct, right? All that you really know is that it seems correct for the inputs that you tried. Right? The question is, one of the long outstanding questions in software engineering is can you actually prove that this program is correct? Right? And the answer is yes, but you have to be able to describe your program in a mathematical way. Right? Preconditions and postconditions are one way to do that, right? Or a part of one way to do that, right? If you can check your code and test that every method is called such that the preconditions are satisfied, right? And if you can test your code that every method correctly satisfies the postconditions, right? Then that goes a long way to formally proving your program is correct. Right? So that's something to look forward to, I guess, in 4th year. There are languages, right? There are languages designed for safety critical applications where you can formally specify preconditions and you can formally specify postconditions. And the language will check, are the preconditions satisfied when a function or method is called? Are the postconditions for the function or method satisfied after the function returns? Right? Java is not one of those languages. Right? But there are languages that actually have all of this precondition and postcondition testing built into them. Okay, so that's all I want to say about preconditions and postconditions for the time being. I do want to talk about another type of condition, though, and those are the class invariants. So an invariant is another kind of condition, right? Invariants are always supposed to be true, right? So an invariant is a condition that's always true. A class invariant is a condition regarding the state of an object that's always true, right? And so there are certain kinds of objects where there are conditions about the state of the object that are always true, right? So point 2 is not one of those classes, right? So the point 2 class has got an x and a y coordinate, but there's nothing special about the x and y coordinate. The counter class, though, so remember this counter class, it's this class that counts from 0 up to some value, right? When it hits the maximum value, it wraps around back to 0. It has a class invariant, right? So you know something is true about every counter object, right? The value of the counter is always greater than or equal to 0. And furthermore, the value of the counter is always less than or equal to integer max value. If you look at the methods in the counter class, right, you will see that every method in the counter class and all of the constructors, right, they all ensure or they all result in this condition being true. So let's look at the counter class. Right, so remember we have a value, right? Now I'm going to check, right? I'm actually going to check, is the invariant always true after every method or constructor runs, right? So if you wanted to do this sort of thing, right, you could insert a little method here called check invariant, right? It's private because nobody needs to know that this invariant is true outside of the counter class, right? In other words, only the counter class needs to check its invariance, right? I want to check, is the value of the counter always greater than or equal to 0? I don't have to check this part of the invariant, right? Because value is always an int, right? And so I know that all ints are less than or equal to integer max value, right? So that part of the invariant must always be true. I'm going to use this thing that I didn't tell you about called assert, right? The way assert works is it evaluates this thing here. If that thing is true, nothing happens. If this thing is false, your program stops with an error, right? It's not quite an exception, but it stops with an error, right? You can turn assertions on and off, right? So if you turn them off, this line of code never runs. If you turn them on, then this line of code runs whenever you call the method check invariant, right? So our counter constructor, it uses constructor chaining, right, to set the value of the counter to 0, right? So the value of the, so this constructor here calls this constructor here, passing in the value 0, right? Now look at what this constructor here does, right? It checks, is the value that's passed in, is it less than 0, right? If it is, it throws an exception, and then that constructor stops, right? If the value is greater than or equal to 0, it sets value equal to value, right? And so this constructor here does in fact ensure that the invariant is always true, right? It only sets this dot value to that as long as that is not less than 0, right? You can check the invariant here, and this will always pass, right? So here's the copy constructor, right? So this is a constructor that copies the value from another counter, right? It does that by getting the value of the other counter and calling this constructor, right? Now the question here is other value always valid, right? And so this constructor should always work, assuming that you've implemented the rest of the counter class correctly. Right? So what I mean by that is, if the counter class actually enforces the invariant that the value of that counter is always greater than or equal to 0, then this line will never fail. Right? The problem is you have to look at the rest of the counter class to determine whether or not this line always succeeds. Right? And so let's do that now. Here's the value method, right? The value method returns the value of the counter, right? So that doesn't change this value. So this will never break the invariant. Right? Here's advance. So this is the one method that might break the invariant, right? If you implement advance incorrectly, you might cause the value of the counter to go less than 0. So check the implementation of advance, right? So if the value is not integer max value, add 1, right? So if your value is always between 0 and integer max value, and it's not equal to integer max value, then you know you can safely add 1 to the value, right? So that line will never break the class invariant, right? Now, if the value is equal to integer max value and I add 1, that breaks the invariant because the value becomes negative. But instead, we set the value to 0, which is also doesn't break the class invariant, right? So advance also succeeds, right? In other words, it never breaks the class invariant. And so those are all of the methods for the counter class, right? We know that all of the methods satisfy or ensure that the class invariants are always true. The constructors always ensure that the invariants of the class are always true, right? And so we can be confident that the counter class correctly maintains its invariant that the value of the counter is always greater than or equal to 0. Oop. Oh, here's toString. I guess you should check toString too, right? toString never changes this dot value, right? And so it too also ensures that the invariant is always true, right? So a class invariant, again, it's just some condition on the state of the object that's always true, right? It's the responsibility of the implementer of the class to make sure that all of their methods and constructors maintain the class invariant, right? If you really wanted to, you could check the invariant in every method and every constructor, right? In Java, you normally don't do this. Right? Again, there are programming languages for safety-critical applications where you can express class invariants, and the programming language will test whether or not the invariants are true after every method or constructor finishes, right? Again, Java's not one of those languages, right? The best you can do is simulate it doing something like this. All right, so that's the end of lecture deck number called Classes 2. And so we're now on to Classes 3. Which is here. Okay. So for this part, I'm going to go back to, so the way the courses work so far is we started out with static methods. You worked with some static methods in classes, and then we made classes that represent objects, and we got rid of the static methods, right? I'm now going to bring back static stuff, static things, right? So static fields and static methods. Right? You can create a class where some of the fields are non-static and some of the fields are static. Right? Similarly, some of the methods can be static and some of the methods can be non-static. Right? So you can mix static features into a regular class. The important thing to remember is that static features, they belong to the class. They don't belong to individual objects. Right? So if you have a static field, then we say that the static field is a per class member, right? There's only one copy of the field. The field belongs to the class. Right? So remember, for non-static fields, every object gets a copy of those fields. For a static field, only the class has a copy of the field. Right? So what that means is that every object that you create using a class that has a static field, right, it ends up sharing, right? It shares that same copy of the field, right? Every object shares that field. You'll often see the term class variable for static fields, right? This is the next set of lecture slides. 13. Right? So class variable to emphasize the fact that the variable belongs to the class. Right? If it's a non-static, then it's often called instance variable, right? To indicate that the variable belongs to an individual object. Whoops, sorry. Okay. For this example, I'm going to use, I'm going to create a class that represents a domino. Now, if you don't know what a domino is, it's just it's a tile in a game called dominoes, right? Basically, you've got a tile. It's got two sides. Each side has some number of what are called pips, right? So that's got 5 pips and 5 pips, right? There's many variations of the domino game. Basically, they involve trying to match dominoes by matching the number of pips on 2 tiles, right? It's in lecture deck 13. They are there. Classes 3, no. This is, I did not, these slides are the same as what are on the website. The standard deck of dominoes looks like, or a standard deck of dominoes looks like this, right? So it involves all the tiles having 0 pips, 0, 1, 0, 2, and so on up to 6, 6. Okay, so for dominoes, right, there's a minimum value and a maximum value for the number of pips, right? So the minimum value is 0 and the maximum value is 6. Right? Now, it doesn't make sense for every domino object to store these 2 values. Right? Min value is a constant, which is why it's static and final. Which is why it's final. Right? It's never going to change, right? The minimum number of pips for a domino is always 0. Right? So you don't need a copy of this field for every domino object. Right? 1 will do. If you make it static, it now belongs to the domino class. Right? The same thing is true for max value. Right? The maximum value for every domino is 6. It doesn't make sense to have this variable in every domino object. Right? 1 instance will do. I can put that in the domino class. Right? And that's why min value is static, and that's why max value is static. Now, every domino object has its own number of sides, its own number of pips for side 1 and side 2. Right? So val 1 and val 2, those are the number of pips for each side of the domino. Those can't be static because every domino has a different number of, has its own number of pips on each side. Right? If you made these static, every domino object would have the same value 1 and the same value 2. Right? So it's really important that these 2 fields not be static. Right? It's useful to make these fields static because there's no purpose in giving every object a field min value and max value. Right? It's just a waste of memory if you do so. Okay, so this is what happens when you make a domino object or 2 domino objects. Right? So domino D1. Right? So remember that does, it makes a variable called D1. Right? New domino 1, 3. So what does that do? It makes a domino object somewhere, which is here. Right? It sets value 1 to 1 and value 3 to 3, right? So val 1 is 1 and val 2 is 3. Now, the rule in Java is when you use a class for the first time, that class gets loaded into memory somewhere. So the domino class appears here, right? I haven't been showing the classes in the memory diagrams, in the previous memory diagrams, right? But now it's useful to know what these do, right? So inside the domino class, right, that's where the field min value and max value lives. Right? Min value is 0, max value is 6. Right? Notice that the 2 domino objects, they don't have a copy of min value or max value. Right? These are static, they belong to the class. These are non-static, they belong to the individual objects. Right? So everything I told you previously about static features still applies. If you want to use a static field, you use the name of the class followed by a dot, followed by the name of the field. Right? So if I want to use the value of min value in the domino class, you write domino.min. You write domino.min value. Right? It is legal, but considered bad form to access a public static field using an object. Right? So you could make a domino object D and then write d.min value. Right? That will work. The compiler probably, I don't remember if it issues a warning or not. Right? Eclipse will tell you, Eclipse will underline it in orange and say, hey, you shouldn't do this, right? But it is legal, right? So don't write that, right? Instead, use the class name. Okay, if you have a field that's final, that means you can only give it a value once, right? And so public static final fields are typically assigned when they are declared, right? And so min value gets the value 0, right? And its value is always 0 in this case.